Chapter 8 is called Analytic Trigonometry, and most of Chapter 8 is going to involve using formulas to simplify trigonometric expressions. 8.1 is mostly concerning the addition formulas. You're going to need to know them, but you don't have to derive them, and then you're just going to do a lot of simplifying, use them, evaluate, and then use some more. And then in the second day we will go into the formulas for tangent, which means in the first day we'll be doing sine and cosine addition and subtraction formulas. The distributive property doesn't always work, so in algebra, if we wanted to distribute a to both terms of this expression, we would have ab plus ac. That doesn't work for functions. So if I need to take the sine for the addition of two angles, I can't just simply distribute sine to the first angle and sine to the second angle. Without proof, you're just going to have to use the fact that sine of s plus t follows this pattern: sine s cosine t plus cosine s sine t. And then there's three other formulas for the sine for the difference between two angles, cosine for the addition of two angles, and cosine for the subtraction of two angles. So moving on to the examples, the first thing we can look at is the question that says simplify sine theta cosine 2 theta minus cosine theta sine 2 theta. And while we might think that cosine 2 theta is where we're going to start, actually this looks more like the right side of one of the formulas. If we go back and look at the formulas, anytime I see sine, cosine, minus cosine, sine, I'm going to think of sine of s minus t. So to start simplifying this question, I have this as my s and this is my t, and if I see sine, cosine, minus cosine, sine, I'm going to think that this can be simplified into the sine of theta minus 2 theta. And again, the first angle is my s and the second angle is my t. I know that theta minus 2 theta is a negative theta, so that simplifies into sine of negative theta. And then from the previous chapter, we know that the sine of negative theta is the same thing as the opposite of sine theta, and that's because sine is an odd function. So this is a simplified version of the original expression. The second question says, how could I simplify a sine function if I move it right 90 degrees? Pi over 2 is 90 degrees. Well, this is not going to be the distributive property, but again a sine subtraction. So again, the formula is sine cosine minus cosine sine. The s I'm going to use is x, and the pi over 2 represents a t. So sine x cosine pi over 2 minus cosine x sine pi over 2. And unlike the previous question where I had unknown angles, I know what the cosine of pi over 2 is, and I know what the sine of pi over 2 is. Since the cosine of pi over 2 is 0, I have sine x times 0. And since I know the sine of pi over 2 is 1, I have cosine x times 1. Well, this disappears. Anything times 0 is 0, and I'm left with a negative cosine x. And that's a simplified version of this question. That tells us that if we took a sine graph and moved it right by 90 degrees or right by pi over 2 radians, I would have a cosine graph that's been flipped. The last one will demonstrate the real power of the addition formulas. 105 degrees is not a location on the unit circle where we have the ordered pair memorized. But since 105 can be rewritten as 60 degrees plus 45 degrees, and since 60 degrees and 45 degrees are both known locations on a unit circle, we can use the cosine addition formula to simplify the cosine of 105 degrees. So my method is going to be, I need the cosine of 60 degrees plus 45 degrees. That's a cosine addition. We know from the formulas that cosine addition is cosine cosine minus sine sine. So I'm going to the cosine 60 degrees, cosine 45 degrees minus sine 60 degrees, sine 45 degrees. All four of these are unit circle locations that we know. Cosine of 60 degrees is 1/2. Cosine of 45 degrees is root 2 over 2. Sine of 60 degrees, root 3 over 2. And sine of 45 degrees is root 2 over 2. Simplifying a little bit further, root 2 over 4 minus root 6 over 4, and finally root 2 minus root 6, all divided by 4 is the final answer for that one. So 3 quick examples of how the sine and cosine addition and subtraction formulas can be used. The next set of examples involves proving cofunction identities. If I take cosine of pi over 2 minus theta, which involves a flip and a shift by 90 degrees, I wind up with a sine function. These are actually identities that are useful. We'll prove one, and then from this point on we'll just use them without having to derive them over and over and over again. Cosine subtraction, the formula is cosine cosine plus sine sine. So I'm going to say cosine pi over 2 cosine theta plus sine pi over 2 sine theta. Pi over 2 is 90 degrees. The x-coordinate at 90 degrees is 0. So this winds up becoming 0 times cosine theta, or 0, plus the sine of pi over 2, the y-coordinate at 90 degrees is 1. 1 times sine theta is sine theta. So our final answer is simply sine theta, and we proved what we wanted to prove. The next set of examples is going to take a while. I'm told that the sine of s is negative root 2 over 5 and that s is in the third quadrant. I'm told that the sine of t is 2/3 and that t is in the first quadrant, and I'm asked to find the sine of s plus t, even though I don't know what angle s is and I don't know what angle t is. So to start with the formula, the sine of s plus t is again sine cosine plus cosine sine. So I know I need sine s cosine t plus cosine s sine t. To find these 4 things, I look at what I'm given. Sine s, I was told, is negative root 2 over 5. So over here I have negative root 2 over 5. Cosine t, I don't know. I wasn't given that. Cosine s, I wasn't given. And sine t, I was told, is 2/3. So in order to figure out the sine of s plus t, I need to find out cosine t and cosine s. Well, if I draw many little diagrams for the 2 pieces of given information, I'll be able to figure out the 2 remaining unknown things. Sine s, where s is in the third quadrant, between pi and 3 pi over 2, tells me that both the x and the y are negative. And if I have that the sine s is negative root 2 over 5, I know that sine squared s plus cosine squared s equals 1. Negative root 2 over 5 squared plus cosine squared s equals 1. I know that cosine squared s equals 1 minus. Squaring this and bringing it to the other side gives me negative root 2 times negative root 2 is 2, and 5 squared is 25. So 2 25ths. I know that now cosine squared s is 23 25ths, which tells me cosine s is plus or minus. The square root of 23 doesn't simplify, but the square root of 25 is 5. And I know that since I'm in quadrant 3 and that both the x and the y have to be negative, I know that my positive version is no good, so I'll cross that out and take this cosine s equals negative root 23 over 5 and put it up there. Cosine s negative root 23 over 5. The next thing and the final thing to do is repeat the process for sine t. I'm told that t is between 0 and pi over 2, which puts me in the first quadrant. X is positive, y is positive. I still know that sine squared t plus cosine squared t equals 1. Filling in the 2/3. Solving. Cosine squared t equals 1 minus 4/9. 2 squared is 4, 3 squared is 9. When I bring it to the other side, it gets subtracted. Cosine squared t equals 5/9. And when I square it both sides, I get cosine t equals plus or minus root 5 over 3. Since I'm in quadrant 1, again, I can get rid of the negative version and just use the positive version. And that goes in the parentheses up here, root 5 over 3. And now I'm finally ready to answer the sine s plus t question. Multiplying the first two together produces negative root 10 over 15. Multiplying the second two together gives me negative 2 root 23 over 15. They both have a common denominator of 15, so it's not that hard to add them together and get negative root 10 plus negative 2 root 23 over 15. The final example involves an average rate of change. I'm asked to find the average rate of change for cosine. This statement here, delta g over delta x, just means find the average rate of change. And from chapter 3, here's the formula for average rate of change for a function f. F of x plus h minus f of x over x plus h minus x. You're subtracting the x coordinates, which the x's will cancel out and you'll be left with just an h. So let's use cosine x in our average rate of change formula. I need to find the cosine of x plus h and then subtract off the cosine of x and divide that all by h. Cosine of x plus h is the addition formula, so I'm going to have to do cosine cosine minus sine sine, cosine x cosine h minus sine x sine h minus the cosine x that was in the numerator to begin with, all divided by h. Now, unlike the algebra examples and the function examples we did with the average rate of change, there's not much simplifying that I can do in this. I'm going to bring the two cosine x's near each other and factor cosine x cosine h minus cosine x minus sine x sine h, all divided by h. So at least I have the cosine x's near each other, so I can factor a cosine x out of the first two. Cosine x cosine h minus 1. And I'm going to put all that over h. And then as a second fraction, I'm going to have minus sine x sine h over h. So minus sine x sine h over h. And that's pretty much as far as we need to go. In calculus, you learn what the next step is. You learn how to simplify this and this using some calc tricks. And the calc trick is basically if you let h be real small, the cosine of a very small number is essentially the same thing as the cosine of 0. And at cosine of 0 we have 1. 1 minus 1 is nothing, so that whole quantity becomes 0, and that whole first term winds up canceling out. The sine of h over h, again, if you let h become real small, both of those get real close but not quite 0, and when they become almost identical to each other, this part here becomes 1. And in calculus you learn that the average rate of change for a cosine function boils down to be negative sine x. But again, you won't have to worry about that till next year. Our job is to just get it into the same form as the green material written up there. So that's it. Those are the first few examples that involve using cosine and sine addition and subtraction formulas. The next part will do the same thing but with tangent.